On the 17th of April, 1943, at a small workshop inside the Power Jets facility in Lutterworth, Leicestershire, the sound of compressed air filled the airframe bay. A cylindrical steel casing lay open on a wooden stand, surrounded by grease tins and micrometer gauges. The light came from a single overhead lamp, swinging slightly as the floor vibrated under the weight of testing equipment. The name Whittle unit for fifths was chalked onto the casing's side, an engine design that few in the Air Ministry still believed would matter. Technicians tightened bolts in silence. Each rotation of the spanner echoed across the room. The casing was heavier than expected, the compressor blades had been widened again. The centrifugal wheel glimmered under the light, crude, but balanced within a tolerance of 0.5 millimeter. According to the test sheet pinned to the wall, the airflow target was 3.2 pounds per second at 17,000 revolutions per minute. The numbers looked ambitious. Beside the sheet, a coffee-stained blueprint showed a revised diffuser pattern, drawn in pencil by Whittle himself. Outside, the airfield was quiet. No aircraft taxied, no engine started. Fuel shortages had reduced testing to a minimum. The RAF had turned its attention to piston engines capable of longer range, leaving Whittle's team to improvise with scrap metal and reworked compressor parts. Yet on that morning, the focus was on airflow, not policy. The instrument technician, J.L. Williams, adjusted the pressure gauge and shouted over the noise, holding at 80 psi. The dial quivered, steady. The airflow steadied into a sharp whine, not the roar of ignition, but a cold, mechanical whisper. In the next room, an Air Ministry observer recorded data with a stopwatch. He marked each reading on Form 2507, pressure, temperature, vibration. No remarks, no speculation. The entry for 1103 read, stable rotation achieved, turbine housing temperature within limits. Beneath it, a note in graphite, design not approved for production. It was a bureaucratic verdict that would quietly bury Whittle's centrifugal concept for the remainder of the war. By that year, the Germans had already flown their axial flow jets, the Jumo 004 and BMW 003, with narrow profiles and linear airflow. The British prototype, in contrast, appeared round and inelegant. It looks like a dustbin, one Rolls-Royce engineer later wrote. But it was the shape that allowed the pressure ratio to rise rapidly, reducing stall risk at low speed. None of this mattered at the time, the priority was simplicity and production speed, not experimental stability. When the test ended, the team left the hangar without ceremony. The engine cooled under a thin layer of frost, the same pattern that appeared on every run. Whittle's notes, written that evening, described it as a satisfactory mechanical test with no bearing failure. It was a small sentence buried in a long technical log, but decades later it would be cited as the moment the centrifugal compressor reached practical maturity. For now, the drawings and performance graphs were boxed and stored in the Ministry's file archive under its unadopted power unit, type W.2 By the time the war ended, the name Whittle would be missing from new jet proposals altogether. Yet within those forgotten blueprints lay the proportions, curvatures, and tolerances that would soon define every post-war turbojet in the world, the silent foundation of the jet age. By 1946, the war had ended, but the sound of turbines still filled British hangars. At the Royal Aircraft Establishment in Farnborough, technicians reopened a stack of sealed Air Ministry crates marked Power Jets Limited, obsolete experimental. Inside were drawings, blade segments, and cracked compressor housings from Whittle's original centrifugal engines. The metal smelled faintly of oil and cold storage. The labels were written in faded pencil, W.2B23. Not proceeded with. Two young engineers, recently assigned from the Jet Testing Division, laid the pieces out on the concrete floor. The older of the two, Flight Lieutenant Arthur Blackmore, took caliper readings while the other compared them against post-war German samples, a Jumo 00 for compressor ring retrieved from a dismantled Messerschmitt Me 262. The difference was obvious. The German design used thin, axial stages in a linear stack. Whittle's prototype looked primitive by comparison, one large centrifugal impeller, heavy but compact, capable of moving air outward rather than straight through. Blackmore noted the weight ratio allowed: 1/3 the parts, half the bearings. The German unit had more stages but was fragile. The Whittle model, though crude, could be built without precision steel, an advantage in post-war economies short of alloys and skilled machinists. "It's an engineer's engine," he remarked. "You could build it anywhere." At that time, Rolls-Royce had already begun adapting Whittle's layout into a production unit, the Derwent and Nene series. Both retained the centrifugal core, enlarged and refined, reaching thrust ratings once thought impossible. According to Rolls-Royce test records, the Nene delivered 5,000 pounds of thrust at 12,400 rpm, using the same basic airflow pattern as Whittle's Lutterworth engine. What the Air Ministry had once deemed too heavy and too simple became the benchmark for early jet transport design. In late 1946, a shipment of these engines left East Kilbride under Ministry of Supply Export Authorization 3E46. The destination, the United States and the Soviet Union, both officially for evaluation. American engineers at General Electric disassembled the Nene within weeks. Soviet engineers under Archival and Vladimir Klimov did the same. The centrifugal pattern, outward airflow from a central impeller through curved diffusers, was replicated almost exactly. Within 2 years, the Soviet Roda 45 and the American J-33 both showed unmistakable traces of Whittle's geometry. Photographs from the Science Museum London archive show the inspection process. In one image, an RAF officer leans over a turbine cross-section, pencil marking the curve of each diffuser vane. The caption reads, "Comparative Study of Post-War Jet Types, 1947. In another, Soviet delegates in grey overcoats stand beside the stripped engine, faces impassive, notebooks open. The museum's report describes the visitor's technical observation in the spirit of post-war cooperation. At Farnborough, meanwhile, Blackmore's team continued static testing of a surviving W.2B core. The intake whined, the turbine howled, and for a brief moment the thrust gauge jumped beyond its expected limit. A line of soot traced the concrete wall behind the stand. "That's nearly Nene performance from a wartime prototype," he recorded in the log. The data sheet shows a sustained thrust of 3,200 pounds, achieved on an engine built with improvised alloys and hand-machined bearings. Across the following months, the old power jet's notes were recopied and catalogued into the National Gas Turbine Establishment archives. Most were never published. Yet, they formed the invisible reference for every early British jet patent submitted between 1945 and 1950. By the end of the decade, aircraft powered by these evolved centrifugal units, the Gloucester Meteor, de Havilland Vampire, and even Canadair's early jets, had established the aerodynamic profile of the post-war era. Each carried within its nacelles the same circular core conceived in Lutterworth's dimly lit workshop. The observers at Farnborough wrote their final entry for the project on the 12th of November, 1946, all tests satisfactory. Basis for further design studies. The term Whittle-type compressor would quietly enter engineering lexicons worldwide, without ceremony, without attribution, but with enduring influence. By 1948, engineering reports began to quantify what wartime intuition had missed. A series of comparative tests at the Royal Aircraft Establishment measured thrust-to-weight ratios, fuel consumption, and maintenance intervals between centrifugal and axial jet engines. The findings were dry, numerical, and quietly revolutionary. According to test report RAE at ENG 4872, the centrifugal units achieved an average of 15 hours between overhauls, nearly double the figure of early axial designs like the Rolls-Royce AJ.65 prototype. Despite being heavier per thrust unit, the centrifugal models showed fewer bearing failures and lower blade stress at takeoff speeds. Their circular housings distributed forces evenly, avoiding the resonance problems that plagued narrow axial rotors. Data from Rolls-Royce's own trials corroborated this. Between April and August 1948, Nene engines accumulated 1,160 flight hours without a single compressor seizure. In contrast, the axial flow Avon, then under secret development, recorded repeated surge events above 11,000 rpm. Engineers described the centrifugal core as forgiving, tolerant of manufacturing variance. The same trait that had made Whittle's engine appear crude was now reinterpreted as robustness. A table from a declassified Ministry of Supply memorandum lists postwar exports by type. Of 527 jet engines delivered abroad between 1946 and 1950, 83% were centrifugal. Nations lacking high-precision machine tools, Australia, Canada, Sweden, and Argentina, all adopted the layout because it worked under imperfect industrial conditions. This quiet global adoption proved the concept's universality. Meanwhile, performance figures told another story. In 1949, a Gloucester Meteor F.8 powered by twin Derwent 8 engines reached a top speed of 600 miles per hour during a ministry evaluation flight. The pilot's logbook simply notes, "No vibration, no flameout, power steady at all altitudes." That entry became the data point Rolls-Royce used to validate its design philosophy, direct descent from Whittle's wartime compressor. Archived correspondence between the Ministry and the Science Museum reveals recognition emerging years too late. A letter dated the 12th of January, 1950, addressed to Sir Frank Whittle, expresses official appreciation for pioneering work leading to modern turbine design. It contains no award, no funding, only a polite acknowledgement that his principles informed present and future developments. Whittle had already emigrated to the United States by then, serving as a research professor at the U.S. Naval Academy. In parallel, American reports from the National Advisory Committee for Aeronautics, NACA, at Cleveland noted similar findings. NACA Technical Memorandum 1224, Comparative Compressor Behavior, Axial versus Centrifugal, concluded that for small to medium thrust classes, centrifugal compressors delivered higher overall pressure ratios per stage and superior reliability in field conditions. Engineers observed that the axial alternative offered advantages only at extreme scale and precision. These observations would later define the dividing line of the jet age. Airliners and early fighters alike, from Britain's Vampire to America's TY-33, relied on centrifugal flow engines. Only after industrial metrology improved in the mid-1950s did axial compressors finally surpass them. But the realization had already crystallized. Beneath post-war production reports and fuel charts lay a consistent pattern. Whittle's so-called simplistic design had provided the jet age with its stable foundation. Every dataset, from thrust curves to wear charts, pointed toward the same truth: efficiency alone had not won the war, endurance had. At the Science Museum decades later, those same test sheets now sit behind glass. The ink has faded, the paper yellowed. Yet, the numbers remain legible: pressure ratio 3.2 to 1, thrust 3,200 pounds, temperature margin nominal. Each value confirms what post-war engineers slowly came to admit, that Britain's forgotten engine was not a relic of failure, but the baseline for the world's first practical jet era. By the early 1950s, the world's skies had become a proving ground for Whittle's principles. In factories from Derby to Detroit, mechanics assembled jet engines that looked nothing alike in branding yet shared one unmistakable pattern: a single centrifugal stage feeding a compact turbine core. the blueprint's lineage traced not to any corporate lab, but to a narrow test cell in wartime Lutterworth. In Britain, the Rolls-Royce Nene evolved into the Tay and then into scaled derivatives for the de Havilland Comet, the first commercial jet airliner. Across the Atlantic, Pratt & Whitney's J-48, a licensed version of the Tay, powered the U.S. Navy's Grumman Panther and Cougar. Its compressor curvature, vane angles, and impeller diameter followed the same mathematics Whittle had drafted in pencil a decade earlier. The official design drawings from the Smithsonian's National Air and Space Archives still bear the notation derived from British Nene core geometry. In the Soviet Union, the Klimov Road 45 matured into the VK-01, producing 6,000 pounds of thrust. It powered the MiG-15, the jet that stunned Western analysts during the Korean War. When captured wreckage from a MiG was examined at Farnborough in 1951, engineers noted familiar engineering marks, identical bearing spacing and diffuser contours. The report titled Comparative Examination of Soviet Turbojet Engines concluded, basic aerodynamic design identical to Nene-Derwent lineage. Britain's forgotten engine had returned under a different flag, reshaping air combat at supersonic margins. At the Science Museum, London, one of the original powered jet's compressors stands mounted beside later Rolls-Royce derivatives. Visitors see a clear progression in diameter and refinement, yet the proportions remain constant. The museum's technical label reads simply, centrifugal-flow jet engine, developed from Whittle design, 1937 to 1945. The understatement conceals the scale of its influence. Official postwar assessments began to recognize the quiet transformation. The 1953 Ministry of Supply White Paper on Aero Engine Development stated that centrifugal designs, initially considered interim, have furnished the necessary bridge to axial advancement. It was an admission that without Whittle's groundwork, the transition to mass-produced jets might have stalled entirely. Industry data from the same period reinforces this conclusion. Between 1945 and 1955, more than 25,000 centrifugal flow engines were built worldwide, powering trainers, bombers, and commercial transports. Their simplicity allowed newly industrialized nations to enter the jet era without the infrastructure demanded by axial designs. Each unit carried the aerodynamic DNA of Whittle's first practical compressor, replicated, scaled, and improved by hundreds of anonymous engineers who never met its creator. Whittle himself, then living quietly in the United States, followed these developments with restrained satisfaction. In a 1957 lecture at the Institution of Mechanical Engineers, he remarked, "It is curious to watch one's own mistakes become the standard practice of the world." The audience laughed softly, the remark entered the record verbatim. The tone was neither bitter nor proud, merely factual. By the 1960s, the centrifugal compressor had given way to the axial giants that powered supersonic flight, but its principles, balanced pressure distribution, mechanical simplicity, resilience to surge, remained fundamental in auxiliary and small turbine systems. Every helicopter, business jet, and auxiliary power unit still echoed the airflow patterns first proven on the test stand at Lutterworth. In retrospect, the phrase forgotten engine becomes a technical misnomer. It was not forgotten, it was absorbed. Its geometry lived on in blueprints, its tolerances encoded into production habits, its lessons carried forward by engineers who never read Whittle's original notes yet applied his logic daily. At the Science Museum, the display lights dim automatically after hours. The metal surfaces of the power jet's core reflect the faint glow of a single emergency lamp. No sound, no motion, only a record card under glass, handwritten and dated the 17th of April, 1943, stable rotation achieved, turbine housing temperature within limits. The handwriting is careful, unadorned. It marks the moment Britain's overlooked machine quietly began powering the modern age. By the dawn of the 1960s, the centrifugal compressor had retreated from the front lines of military aviation, but not from engineering. While supersonic jets demanded the thin axial profiles of the Avon, Olympus, and J-79, Whittle's geometry endured in quieter, smaller systems, the heart of helicopters, auxiliary power units, and compact business jets. Its survival was not nostalgic. It was practical. At Rolls-Royce's Derby facility, engineers used Whittle's flow equations as reference data for side projects, lightweight turbines intended for naval generators and rotary wing aircraft. The resulting engine, the Rolls-Royce Gnome, first ran in 1958. Its compressor section still followed the outward flow curve of the powered jet's W.2b. Air entered through a single impeller, expanded centrifugally, and was diffused into the combustion chamber through a ring of curved vanes almost identical to those Whittle had hand-drawn 15 years earlier. The lineage was clear enough that test engineers called it the Whittle core. In the United States, Garrett RA Research refined the concept into a series of small turbojets for auxiliary power. The Garrett TPE-331, first tested in 1961, produced barely a tenth of a fighter's thrust but demonstrated extraordinary reliability, an engine that could start, run, and restart thousands of times without surge. The engineering memorandum describing its airflow path used the same phrasing as Whittle's wartime notes, radial outflow through diffuser cascade. Even when technology advanced, language remembered. Archival design reviews at the National Gas Turbine Establishment confirmed that Whittle's mathematical constants, blade tip speed limits, diffusion factor ratios, and angle of incidence corrections were adopted wholesale into post-war standard tables. By the 1970s, they appeared in every international turbine manual from Bristol Siddeley to Pratt & Whitney. Engineers who had never heard Whittle's name still worked under his constraints. The principle of compact, rugged compression re-emerged with a new identity in the turbofan era. The high-bypass engines that powered airliners like the Boeing 747 contained within their core a small centrifugal stage for internal air systems, a miniature of the Lutterworth concept buried deep inside massive axial cascades. The structure of modern aviation, from the smallest Apus to the largest passenger jets, thus carried a hidden continuity, axial thrust-powered flight, but centrifugal flow powered everything that sustained it. Museum collections today trace this continuity with precision. At the Science Museum London, the Whittle unit for fifths sits beside a Nene, a Gnome, and a Garrett APU. A small placard connects them with one sentence, all derived from the 1937-43 Centrifugal Studies of Powered Jets Limited. The engines vary wildly in size and shape, yet when viewed from above, each reveals the same circular pattern of vanes, a fossil record in metal. In 1976, when Whittle received the Order of Merit from Queen Elizabeth II, the citation described him as the originator of the gas turbine jet propulsion system. The ceremony lasted 8 minutes. No mention was made of the centrifugal compressor, nor of its spread across continents. Yet in the audience sat engineers whose entire careers rested on it. Decades later, aerospace historian Andrew Nahum summarized the irony in a Science Museum monograph. The centrifugal compressor, dismissed as a transitional curiosity, in fact became the most copied and longest-serving jet configuration in history. His conclusion was not poetic, it was statistical. Production records showed over 40,000 engines based on Whittle's geometry built between 1943 and 1980, more than any other single-jet configuration. In laboratories, the equations still appear. Airflow coefficient, pressure ratio, diffuser efficiency, the same variables Whittle scribbled in the margins of his notebooks. When students plot those curves today, they reproduce a wartime insight unchanged by 70 years of progress. The legacy of Britain's forgotten engine therefore lies not in museum glass but in method. Its design proved that simplicity could achieve endurance, and endurance could shape an entire technological century. Each modern turbine that spins quietly at altitude still carries, unseen, the echo of that first compressor at Lutterworth, stable, balanced, and infinitely repeatable. In 1986, for decades after the first power jet's engine had been boxed and labelled unadopted, the Science Museum in London opened a new exhibit titled The Birth of the Jet Age. At its centre stood the same compressor that once shuddered on a test stand in Lutterworth. Its casing was polished now, its edges restored. The museum's lighting technician set a low amber hue to simulate the workshop glow of 1943. Visitors read the small printed card beneath, donated by Sir Frank Whittle, 1948. Operated successfully at 17,000 RPM. Behind the display, a single black and white photograph shows Whittle in uniform, sleeves rolled up, leaning over a half-assembled turbine. The caption gives no biography. It does not mention that he was dismissed from power jets in 1946 or that his concept had been revived without credit in every major air force. The curators chose silence over sentiment. The facts, arranged in sequence, told the story themselves. During those same years, aerospace engineers began digitizing pre-war airflow data for modern computational models. When the first digital simulations of centrifugal compressors ran on IBM mainframes in the late 1970s, the results matched Whittle's hand-calculated pressure curves within 2%. His equations, written with a slide rule, proved as accurate as electronic computation. The validation came too late to matter to policy, but not to history. In 1987, the Royal Aeronautical Society issued a retrospective citation describing Whittle's compressor as a geometrically elegant solution achieved under wartime constraint. The phrasing was deliberate, technical, not emotional. The document did not praise, it confirmed. That tone suited Whittle's own view. When interviewed for a BBC science programme that same year, he said simply, "I built what was possible, not what was fashionable." His voice was calm, almost detached, as if describing an equation rather than a revolution. By the 1990s, scholars reviewing Cold War engine development traced an unbroken chain from power jets to every subsequent turbine lineage. The Soviet Rode 45 to VK-1, the American J-33 to J-48, the British Nene to Tay, the French Hispano-Suiza Nene clone, all stemmed from the centrifugal archetype. In total, more than 50 nations had operated aircraft powered by direct or derivative forms of Whittle's engine. The discovery reshaped historical credit. This forgotten engine was no longer forgotten, only assimilated beyond recognition. In 2002, engineers from Rolls-Royce and the Science Museum restored the original Whittle unit for fifths to static display condition. The restoration report notes minimal corrosion inside the compressor casing and near-perfect balance of the impeller after half a century. It still met the original design tolerance of plus or minus 0.5 mm. The record concludes dryly, unit remains mechanically sound for rotation. The understatement mirrored the entire story, precision without drama, endurance without applause. Today, when aviation students walk through the museum's flight gallery, they pass the Whittle engine without ceremony. Few notice the faint inscription scratched near its intake lip, W.2B 700, April 1943, stable. The letters are nearly invisible, worn by decades of handling. Yet that inscription captures the threshold of modern propulsion, the moment when a hand-built prototype proved that jet power was not theoretical, but practical. Measured against the roar of later engines, the power jet's unit seems small, almost modest. But its design, one disc, one flow, one idea, remains embedded in the DNA of every turbine that followed. The post-war engineers who once dismissed it later adopted its logic by instinct. The nations that borrowed its design built their air forces upon it. And the institution that once filed it under obsolete now displays it under origin. The room is quiet. The compressor no longer spins, but the geometry endures, a perfect circle that once drew in air, and with it, the future.